we'll go ahead and get started. If Eric comes in, he'll have only missed the very beginning. Now, at the end of the period today, I'm going to hand out the tests. And remember, we're doing the test as a snow day, so you get to take home the tests and so on. Hypothetically, that means you would have until next Tuesday to do it, but that's really not appropriate for a take-home test. We'll probably say that the tests are due on Friday, okay, because we have this class on Friday, don't we? Yeah, I believe that's what we do. So we'll probably say that they're due on Friday. That way, in case there's any problems on Thursday, you can take them home. You got a question, Jared?
Yeah, I may or may not be here because...
On Friday?
Yeah.
Okay.
Only because one of my best friends is having surgery.
Oh dear. Okay.
Having gallbladder surgery.
You could bring it on Thursday.
Got it.
Okay. All right, so we've got that under control. I'll give you guys the test. It seems a little thick, but it's partly because a lot of the questions either have a figure, that takes up a ton of space, or they're multiple choice, and that kind of takes up a bunch of space for not that much thinking. So I mean, it's like 7 pages or something, which seems a little big, but that's just the way. Just the way it was typeset. Okay. All right, now we're going to move on into chapter 3. We actually get to start doing some calculus stuff, and we can thank these two bigwigs for that. That's Leibniz and Newton, both of whom invented calculus completely separately in the 1660s. And Leibniz was a German mathematician, and Sir Isaac Newton was, British guy, apple fell on his head, all that kind of thing that didn't really ever happen. And they both needed calculus, and they both figured it out about the same time, mathematically how it would work and so on. It's not entirely fair to say they invented calculus because a lot of the ideas, especially with the part of calculus that's about figuring out the area under curves, namely integrals, had actually been kind of thought through by like Chinese mathematicians and Arabic mathematicians and so on to good approximations before that. But these were the guys who really figured out a systematic way to do it all and so on. Leibniz is the guy who came up with most of the notation. Newton was in general a crazy person, and his way of actually writing it all out isn't very helpful. But Newton actually invented it a few years before Leibniz. All right. We're going to be working today, really this whole chapter actually, is about the idea of a derivative. And derivatives are going to be about that whole idea again of tangent lines. Now, remember, was that chapter 1? No, that was the beginning of chapter 2. We had a day that was like, what calc is going to be all about. And we learned about this idea that we could make a function. The idea of the slope of a line is a useful thing. If I try just drawing something over here real quick, if I just make, a function, it's a useful thing to know what the slope here is. Again, if we draw ourselves apparently a school bus on there, we would need to know what the slope he's driving up is. Okay, that's not exact. But, this could be, for example, the temperature of some object, and knowing the rate of change, like this is time going this way, and this is temperature here. So this is warming, this is at the same temperature, this is cooling, then it's at the same temperature, then it's warming. Knowing the rate of change, or the slope of the function, is a useful thing. And we kind of just played with the idea a little bit back in section 2.1, where we said, what we really mean is we want the slope of the tangent line, where the tangent line is that line that only touches the equation just at that one place. A difficult thing to actually to draw without thinking through how calculus is going to do it, but we were able to make approximations to that line by talking about the secant line. Where if we're talking at some point A, where x is equal to A, the slope at this point here, this tangent, could be approximated by the slope of this secant line, where the closer and closer together, it's touching at 2 places here, but the closer and closer we got, x and A together, the closer that secant got to the tangent. In fact, we had an equation for that. Let me blow this up a little bit here. I think I can zoom this up just to make it a little bit bigger. Yeah, that'll help. We actually even had this equation back in 5.1. I'm sorry, 5.1, not the other class. In 2.1, where, okay, the notation's a bit weird. By m sec, they mean the slope of the secant line, thinking in that notation that slope is m, as in mx plus b. Where the slope of the secant line at some point A, like at some point A, is this function here. Where we have, let me draw another one over here. We're getting a little crowded here, so let's make this clean it up a little bit. Where the slope of the secant line at some point A, and you've got some other point here, x, here's your secant line that goes through those 2 points, is just f of x minus f of a divided by the difference between x and a. There was a second way to write it, and the book goes over the top on this. But just to be clear, another way to write it would be to talk about x and a as like how far apart x and a is, and calling that difference, they're going to use the symbol h here. So like h is this little distance between a and x. And then they could rewrite this as like f of a. Well, f of x is just f of a plus h. That's how far apart x is h from a. And you can simplify it and write it this way. The book is going to make a big deal about the fact that these two things are equivalent. That you could talk about the slope of the secant line in either of these two forms. It's going to call one of them 3, 3 and one of them 3, 4. But we'll get there in just a little bit. But either way, the slope of the secant line would just be related to the values of f of a and f of x, and how far apart a and x are. So as a and x get closer and closer together, we'll be getting closer and closer to the actual slope of that tangent line, that rate of change at that place, that derivative. Alright, so your book then introduces a notation that I don't think they come back to, at least not for a while. I do want to at least point you to it. They call that ratio there. Oh, wait. Sorry. There. They call that ratio f of x minus f of a divided by x minus a. They call it Q, the difference quotient. Whatever. It's a ratio of two differences. It's a quotient of two differences. All right. And they just have two ways of writing the same thing. This one and this one, where this one they use those h's, and here they're just saying, no, x minus a. But x minus a is h. And the closer and closer those x's and those a's get, that is to say, the smaller that h gets, you're getting closer and closer to the tangent. Well, now that we are survivors of chapter 2, we know where this is going. We're going to be taking this value, we're going to say, as that x gets closer and closer and closer, and our secant line is getting closer and closer and closer to being a tangent line, that is to say, we're going to have a limit as x approaches a, or as h, the difference between x and a, comes to 0, that's going to be the slope of our tangent line. And again, they work through all these, like, you know, oh, look, we're getting closer and closer. If you look through this book, you're fine. Now, in other words, I like this one right here. That's my favorite one. The slope of the tangent line, which they're writing right now m tan, the slope of the tangent line at point A, then would be that same quotient, that same difference ratio, f of x minus f of a all over x minus a. That's the slope of the secant line. The limit as x gets closer and closer to a will be the tangent. If we can compute that limit using the big skills that we learned in chapter 2, we have the slope of the tangent line. Not an estimate of the slope of the tangent line, the actual slope of it. Or we could do the same thing over here using that h definition, where h is x minus a. So as that difference gets smaller and smaller, then we are getting to that tangent. Again, not an approximation to the slope, that is the slope. Now, you're going to have a test that you're taking home with you to remind you about limits, but to be honest, the limits chapter got a little out of control. There was too many different little details. We can kind of keep this a little bit more on the intuitive definitions and so on, let's actually do some of these guys right here. Okay, again, those things are defined right here, where the slope of the tangent line is that limit. All right, so there's actually a blue box with it. Here, let's do an example. I like this one. This is example 3.1 in your book. It says, find the equation of the line, which we'll first need to have the slope of the line, tangent to this graph, f of x equals x squared, at some point, x equals 3. Let's real quick think what this is. What does a graph of f of x equals x squared look like? What is that shape? If we made a graph of f of x equals x squared. It's a line, it's a circle, it's a parabola. Yeah, and it's a parabola up. It's going to be something like this. And somewhere over here at x equals 3, we want to know what this slope is right here. Alright, let's use one of our definitions of what the slope of the tangent line here is. The slope of the tangent line is defined to be, well, one of the definitions was, it'll be the limit as x approaches that point that we're looking for, which was a. In this case, a is equal to 3. Alright, of f of x minus f of a, where a is 3, all over x minus a, where a is 3. Alright, let's plug in some values. F of x is x squared. F of 3 is, plug in 3, 3 squared is 9. All over x minus 3. Hey, if we factor that bad boy, x minus 3, this thing right here becomes x minus 3, x plus 3. Now, back in chapter 2, we would have gone a little bit nuts about this. Because remember, we would have said the problem is at x equals 3, there is no solution. Well, we have one of those kind with a removable discontinuity. But that didn't mean the limit didn't exist. The limit's still fine. It was just that there is a removable discontinuity in this particular one. But I can see, look, this is going to cancel out. This is the limit as x approaches 3 of x plus 3. Well, gosh, that's just a polynomial. We learned back in chapter 2, polynomials, the limits are no problem. Just put the limit in. I mean, if the limit is 3 here, then put that limit in. 3 plus 3 equals 6. Or go crazy, go nuts, and make yourself tables like you did back in, I don't know, section 2.2 or something. You know, put in values that get closer. 2.9, figure your f of x. 2.99, and figure your f of x. And 2.999, and you'll see that you're approaching 3. But we don't do that anymore. We know that for polynomials, you know, it's just x to some power plus x to some other power. In this case, just x to the first power. We just plug that limit in, 3 to the x, and 3 plus 3 to 6. No problem. In other words, the slope of this tangent line, right here, the slope of this line is 6. We aren't ready for that term. Well, we're kind of ready for that term. That also means the derivative at that point is 6. Okay, but we're going to get there just a little bit. Now, that isn't actually what the problem's asking for. What the problem's actually asking for is the equation of the line. That could be hard. Because the book doesn't exactly tell you what to do with that. What they're saying is, okay, what is actually the equation of this line that goes through, you know, well, actually, we know its slope, and we know it goes through this place right here, where x equals 3, and y equals, I guess it's 9, because the function is f of x equals x squared. The text, anyway, doesn't come out and say, but there is a simple way to solve that problem. You could go ahead and use the so-called point slope version of the equation. If you plug in y minus this point up here, if we call this point x1, y1, y minus y1 equals your slope times quantity x minus x1, this will work. So y minus 9 equals our slope times x minus our x. Feel free then to do all your rearranging voodoo, algebra like you've been great at since like 9th grade. And you can make that however you want it to be, like y equals mx plus b kind of form. Okay? It's just a little bit of rearranging and factoring and stuff like that. Which they proceed to go and do, and they get this. Notice the slope is what we said it should be, 6. But you don't very often have to do and find the equation of the line. Most of the time the slope is what you're looking for. Because the slope is the derivative, and there's a million interesting things we can do with the derivative. And we're going to be doing more with that in coming days. But in the meantime, I want to keep looking at some more of these examples here. Let's do this same one. This is the same problem we saw before. F of x equals x squared at the value x equals 3. This is the same sort of problem, except instead this time they wanted to use the other way of deriving the slope of the tangent line, where instead we're talking about it in terms of h, where h is the difference between x and a, and they plugged in the same. They plugged in f of h. They plugged in f at the value of a, and they worked through, and you get the same answer is what they're showing here. So that, which they call 3.3 and 3.4. By the way, I don't know if you've noticed, but any of these orange things are clickable. So you can actually pop yourself back to look at equation 3.4. Okay. Alright. They just showed it could be done both of the ways. Both the equations would be fine. We've already done an example where we found the equation of a tangent line, but you know what? I want to do another one just to make sure we're on the same page about this. So here is the function they're trying to do. Their function that they make a graph of is 1 over x. And they want to know what is the, well, they're looking for the equation, but we'll settle for finding the slope for right now, of that equation at the point x equals, at the value x equals 2. Hey, wait a minute, what does this thing look like? What does a graph of 1 over x look like? I mean, remember, f of x equals x squared was a parabola. What's the word for a graph of 1 over x? What shape is that? Isn't that a hyperbola? Yeah, they look like this and this. Yep. And at x equals 2, this is where we're talking. We're talking about the point right there. All right. So let's do that definition of the slope of the tangent line. We're using the version 3.3. So again, you can touch that equation and go and see what that equation was again. But it's f of x minus f of a over 2, x minus a, where a is equal to 2. Plug that in. The limit as x approaches 2 of f of x minus f of 2, all over that. Voodoo math, voodoo math, voodoo math, until you eventually get something over here. Now again, we would have had some issues with this back in chapter 2. Back in chapter 2 we would have said, aren't we dividing by 0? I mean, at the limit of x is going to 2, 2 minus 2 is 0. We're dividing by 2, 0. Yeah, but okay, if we did some factoring here and simplifying this is equal to this, well, that's just a polynomial. Strictly speaking, it's a rational function, because it's a ratio of two polynomials. But we know that those are okay. We can go ahead and plug in the limit into x, and we just get negative 1/4 in this case. That is the slope of the tangent line. So this slope right here at x equals 2, this slope is negative 1/4, which looks pretty good on my graph. That makes me happy. I would agree with that. Now the book says take it one step farther and go ahead and put in and find the equation of this line. Well, we know it goes through this point here, x equals 2, y equals 1/2. So then we would plug that in, y minus 1/2 equals negative 1/4 x minus 2. And then you would do all your voodoo of algebra distribution and stuff like that to get it back into y equals mx plus b form. Okay, this is not so bad. This is not so bad. I mean, compared to the limit type stuff that we did back in chapter 2, this is actually pretty basic and pretty straightforward. And here's the deal. This is actually what we're calling the derivative. The derivative of a function at a point is just the slope of the line at that point. So we could talk about this, the derivative, this marker's not so great. The derivative of f of x equals 1 over x at x equals 2 is negative 1/4. It is the slope of the tangent line at that point. I've always thought this word derivative is a little bit awkward. I mean, a derivative means it's something that is derived from it. It means it is something, it's something we're extracting from it. Okay? It is something we are pulling out of the function. Alright, if that's our derivative. Now later we're going to learn derivatives aren't just something at some point, the way this is. Notice that the business end of this thing here is this at this point, or the derivative of the function at this point. Later we're going to find out that the function itself, f of x equals 1 over x, has a derivative. And it's a way of describing its slope at any point. Or f of x equals x squared has a derivative. But right now we're just doing the derivative at some point. What is the slope at that point? There's a notation that the book is introducing here. The derivative of, so if you have a function called f of x, the derivative of that function is going to be written f prime, with that little tick mark in there. So we are saying that the derivative of f of x is f prime of x. And right now all we're doing with this is finding the derivative of x at some point. So like it'll be the derivative of f at x equals 2. That's just the slope of the function at x equals 2. It's something we have derived from the function. We have obtained it from the function. So our function was f of x equals 1 over x, and we have derived from it that the slope, the derivative, is, in this case, negative 1/4 at x equals 2. It is less clear at this point why the noun for what we are doing is differentiation. Finding the derivative is called differentiation. It comes from the fact that that word is, we're finding differences. Remember, Q was that difference ratio? This thing right here is a ratio of two differences. The word differentiation comes from that. Okay, but it's not quite clear yet why that's called differentiation. So, but making sure that we understand, because here's the deal. I know that on this and future homework sense, it's going to say things like, find f prime of x by differentiation. Okay, so you need to know that word. Or differentiate f of x in each of these problems. Okay, you got to know the vocabulary here. So the action of finding the derivative is called differentiation. Neat. The book actually has you do some thinking back to the way you used to do limits back in chapter 2, where you've made some of them with a table. And that's neat, but we're not going to be doing that going forward, so I don't have any of those on the problem set. On the other hand, we can certainly do other ones, like this one. Let me figure out which number this is. I want to give you the wrong information. This is example 3.5. In example 3.5, here's your function. F of x equals 3x squared plus minus 4x plus 1. And it wants you to find, notice the notation here, f prime of x, f prime, so the derivative at the value x equals 2. Okay? From our definition of what we meant by f prime, the derivative of f, at the value 2, that means it's the limit as x approaches 2 of that difference ratio. Okay. F of x is just this, minus f of 2, which if you plug it in is 5. Simplify, 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 rearrange, factor. Oh look, we have two terms that can cancel out. Now we just have the limit of a simple little polynomial there. And we know from chapter 2 that all we have to do now is say, okay, this won't have any discontinuities or anything like that. The limit is just plug this number in for x. 3 times 2 plus 2 is 8. Therefore, the derivative of f at x equals 2 is 8. Whatever that function looks like, 3x squared minus 4x plus 1, its slope at x equals 2 is 8. Woo, we can do a bunch of these, but we're going to get even better ways to solve these kind of problems. Alright. Your book takes some time to actually tie this to physical ideas like velocities and rates of change. Like earlier when I was showing you, if we said this is a graph of temperature, I'd be talking about how much it's increasing, how much the temperature is increasing with respect to time, how much is decreasing with respect to time, etc. You know what? There's going to be plenty of opportunities later when we're better at computing derivatives to be talking about derivatives that way. Because here's the deal. We're about to forget about that whole limit way. Notice how we're tying derivatives, rates of change, to limits. But we're soon going to have bigger, better brains, and we won't need that anymore. We'll be able to do derivatives a smarter way, a better way. So we are not going to do that part of the chapter right now with those applications like those, the rates of change and velocities, which are rates of change of positions and so on. And once we're past that, let me just double check. I don't think there was anything else I wanted to do. No. Now we're just ready to do the exercises, which were page 228. Numbers 1 to 29, and you got to show your work. Alright, so page 228, numbers 1 to 29, show your work. Jerry, do you have a question?
I did, but I'll think about it.
Okay.
Before I ask.
Alright, fair enough. Alright, so you're going to be doing a bunch of work using the limits, but not as crazy detailed as you did back in section 2.5 and so on, where you were like epsilon delta definitions and so on. We're not coming back to that anytime soon. Alright, this is a fairly loose idea of limits that you kind of had from section 2.2 and so on. We're going to be tying it to this idea of derivatives, and then we're going to go nuts and look at all this good derivative stuff coming. Oh my goodness, this chapter's huge. 3.2, 3.3, all the way up to 3.9. Does it go even farther than that? Nope, 3.9 is the end of that chapter. Alright, so you got all that. Let me give you the tests as well. And you can have this. Again, I'd recommend getting at least, trying to do the test between now and Thursday so that you can ask me questions on Thursday. And we can, talk a little bit about it or whatever. But I don't think the test is too bad. It's mostly chapter 1. Or at least most of the points come from chapter 1. Alright, I'm going to turn this off.